So we are talking about this guy's principle. I did this morning. Got a kick out of it. See if I can get it to work. Did it work? No, it didn't.
Le Chatelet's principle.
Whoop.
Le Chatelet's principle. Le Chatelet.
Yeah, you can't hear it. Let's try it again.
Le Chatelet's principle. Le Chatelet's principle.
So stick in your head.
Le Chatelet's principle. Le Chatelet's principle. Le Chatelet's
I had nothing else to do this morning. All right, that's how you should pronounce it. But I think that the real official way is this way. This is a French dude actually saying it.
Le Chatelier.
That's how you're supposed to say it.
Le Chatelier.
So anyway, what does this have to do with anything? Has to do with how things get to equilibrium or if they're at equilibrium. Does anybody know? If they're at equilibrium. So pretty much, like here we're talking about the carbon cycle, or you have a can of Diet Coke. If you wait around long enough, pretty much everything's at equilibrium. But then you can mess with it, right? Things change. So if it was at equilibrium, what is it going to do to reattain equilibrium? That's this guy's principle, okay? That's what it's all about. So it has a lot of impact on a lot of different things in life here. So what is it? Here's my pen. Let's start out by writing an expression for Kc. So Cameron, how would you write an expression for Kc for that reaction?
For the top one right there?
Yeah, the Kc. How would you write it?
It'd be D over, you wouldn't put
In dn
brackets.
brackets, yeah.
And then you wouldn't mess with the C because it's solid. Right?
Exactly.
And then you would put A on the bottom.
Yeah.
In brackets with the B brackets.
And has to be, B has to be
It's a 2. You have to
with
have
a 2.
on it.
Yep, there it is. So we wait around long enough, it's at equilibrium. Okay, so if it's at equilibrium, Bowdy, that means these concentrations, D, A, and B, they're not changing over time. Who knows what those numbers are? But they're each a number, and they're not changing over time. So you divide those concentrations out, make sure you square B, and you always get this constant K. So you measure all those concentrations, and you get K. You know you're at equilibrium. What could happen, Bowdy? What could you actually do to mess this thing up so that you wouldn't be at equilibrium anymore? What could you do? Has to be something so you don't get Kc anymore. What could you do? What could you do, Jose? Add something. Okay, what could you add? Increase the concentration of any of them, really, yeah. Increase the concentration of D. So you take some D, dump it in there. Now, this is too big. Your K is going to end up being too what? If you go and calculate K now, too big, right? Because D is too big, so that means K is going to be too big. Okay, so this is, since you didn't get K, you're not at equilibrium. What else could you do to mess with Megan? Add some heat. Ooh, there's a good one. Okay, because heat, really, Alyssa, is a reactant or a product? This is product. She said it pretty confident. Everybody agree? Jose doesn't. Heat is why is it a reactant? Exactly, because it's an endothermic reaction. We have a positive sign. Okay, so it's heat's over there. So Megan said add some heat. So we're supposed to think of heat as a reactant or product, and we did. So heat's over here. So now, Audrey, you almost have to imagine this beaker sitting there. Now all of a sudden you take a flame and you put it under there. You're adding heat. It's not at equilibrium anymore. In fact, things are going to shift in which direction. This is where Le Chatelier's principle comes in. Things are going to this equilibrium is going to shift towards the reactants or towards products to get rid of that heat. It's almost like you have too much on this side. So, well, heat is towards the products because heat is a reactant, and reactions can't distinguish. Just like K's, they can't distinguish between the different products. Can't distinguish between the different reactants. All you know is that it's a reactant or a product. So heat is a reactant. You have too much reactant, it's going to shift towards products, which is a good thing if you wanted to, if A and B are really expensive, and you want this stuff to react, man. You forked out all this money for A and B. You want to get as much product as you can. Well, heat the crud out of it, right? That'll drive the equilibrium to product. That's Le Chatelier's principle, and that's how you make big money on this stuff. Okay, so what about the story with D? I think Bowdy said add some D. That's going to actually cause the equilibrium to shift in which direction? Towards playing this game towards reactants. Because now you've got too much product. It's going to shift it towards reactants. So if you didn't want things to react, just have a lot of D in there. Okay. There's a trick in here. Andromeda, you see the trick question? You could add this, and it's going to have no effect. What compound in that reaction could you add, and it has no effect? C, because C is a solid. It doesn't show up in the K expression. It doesn't matter how much is there. You can keep dumping in that solid. Doesn't matter. Okay. Let's see if we can play the game. There's going to be a lot of homework like this. So what I want you to do is look at, here's the reaction. A plus B goes to C plus D. And it's an exothermic reaction. Here's all the parameters that they're going to do to change to mess with the equilibrium. And what you're supposed to do is say, okay, if I remove some A gas, you write, oh, I'll get more or less D. Remove some C. So just write more or less D next to each parameter there, what you predict, and then we'll ask somebody. More or less D. On each one of these, you can circle your answer. So Mia, what would you guess for A? We're going to remove some A. Would you have more or less D then? What would be the effect? Less D? Not sure? Can anyone help her out? She's lost. Because she's probably not the only one. If I take away A, right? Then it's almost like there's a couple ways you can think about it. If I take away A, then it's like having a hole on the reactant side. I got to fill it. The only way to fill it is by having C and D react, right? Having that dynamic equilibrium shift, right? Because you took away some A. A had the right amount. It was that equilibrium. Just the perfect amount. But then you took some away. And it really doesn't matter what reactant you take. I mean, you take some reactant away, you got to get it back.
So you're going to have more D?
How do you get more A? How are you going to get more A?
You got to have those two products react.
You got to have those two products react. Well, if two products react, the amount of those products is going to go
Up, down.
right? If this is a cookie, I'm the other reactant. The cookie's a reactant. I'm a reactant. We're going to react. We're going to end up with more cookies or less cookies.
Less cookies.
That's obvious, right? Less cookies. So if I want more A, these guys got to react. The equilibrium is going to shift in that direction. It has to. If I remove A, it's kind of like saying, just kind of erase it and say, yeah, it's not there anymore. I got to generate it. In fact, I got to generate the exact amount so I can get that K expression again. What's the amount? Who cares? We just want to know direction the equilibria shift. Okay? That's all we're after. That's all the Le Chatelier's principle's after. So everybody, at the same time, what's the answer to A?
Less cookies.
Perfect. Less D. All right. Oh, man, the pressure is on. Steph, you're going to remove some C now. So let's get this back to where it was. We're going to remove C. What will be the effect on D? More of it. Does everybody agree? Because now you've got a hole here, and you got to get, remember, you got to get that K expression. Well, it doesn't work. There's no way it's going to work with nothing for C, or not enough for C. You got to increase it. So that means the equilibrium is going to shift in this direction. So you're going to get more D. In fact, if you take away C, is the thing going to get hot? There's a good question. If you take away C, will this thing get hot? Yes, because heat's another product. Heat's just like D. It's a product. So if you take away C, it's going to shift. It's going to force A and B to react. Okay. Okay, now these are tricky. Jose, you lucky guy. We're going to add an inert gas to increase pressure. Well, you got a 50-50 shot at this. I guess we should have another choice, no effect, right? Inert gas to increase pressure. Now, there's kind of a trick to this. If you have a little, this guy is happening in a bottle, and you have a little pressure gauge. D is a gas, so D exerts pressure. Does this pressure gauge read only the pressure due to D? I read the pressure due to all the gas molecules, right? So that's pretty much what you got to figure out. You got to figure out the reactants and the products and look at, okay, which side has more gas molecules? And these are hard ones. How many gas molecules are on each side? There's 2 gas molecules on each side. So that means you can do whatever you want to the pressure. The system can't respond. There's nothing it can do. And we're going to do another one after this where it will influence it. But there's no effect because they have the same number of gas molecules. There's no way, because if the pressure is too high, the system, it wants to relieve this extra pressure. Just like if you remove some C, that's a stress. It wants to remove that stress by making more C. Add inert gas, it wants to relieve that pressure, but it can't. There's nothing it can do. How it's going to do it is just have one side that has less gas molecules. It's just going to shift to that side. That's all you're going to do to answer the question. If you crank up the pressure, it's got to relieve that pressure. So you just got to count the gas molecules, and it shifts to the side with less gas molecules. That's the trick to answering that. How about the last one? We're cranking up the temperature. Andrea, we forgot to write no effect. That's supposed to be a possibility. We're increasing the temperature. More or less D? Increasing the temperature is like adding what? Adding heat. So just figure out what side heat's on. Heat's on the product side. So that means we have too much product or reactant. We have too much product. So Le Chatelier says if you got too much product, you have to shift towards reactants. So it's going to be less because D is on the product side. Exactly. That's the logic that I have to follow every single time, even though I've been doing this for years, is figure out where things are at, whether they're reactants or products. So if you have too much reactant, it's going to shift towards product. If you have too much product, it'll shift towards reactant. Doesn't matter what it is, unless it's a solid. Okay, try this one. Well, more or less, another option is no effect. So now we want oxygen gas. More, less, or no effect for each one of these. Okay, let's pick on somebody here. Cameron, I'm going to remove some diphosphorus hexoxide. Will I end up with more or less oxygen?
You're going to end up with less oxygen.
Less. Perfect. How about Bowdy? I'm going to remove some solid phosphorus. Say it louder. Confidence. No effect because it's a solid. Okay, now the fun ones, Megan. We're going to add an inert gas to increase the pressure. She says less. I hear no effect. I hear less. Any takers for more? It's either less or no effect. One of those is right. Okay, let's take a look over here. How many gas molecules are here?
3, 5, or 1.
1. You're just adding up the stoichiometric coefficients, right? There's 1 gas molecule over here. How many gas molecules over here?
3.
There's 3 gas molecules. Okay, so if I cranked up the pressure's too high, system wants to respond by reducing the pressure. If you have the same number of gas molecules on both sides, or you have no gas molecules on both sides, whatever, then the answer is right. There's no effect. But since they're different, oh man, something's going to happen. It has to respond by generating less gas molecules, right? It wants to shift to the side with less gas molecules to relieve that pressure. And that's going to be reactants, so she was right. It's going to end up shifting that direction if you crank up the pressure. Whoop, that's the wrong one, this one. One more here. Kendall, increase the temp. More or less oxygen?
It's going to be, since we're adding, it will be less.
Is less. Everybody agree? I hear more. Write the word heat where it belongs. That'll help. Write the word heat on reactants. Let's erase this stuff. Write the word heat on reactants. And then it's a lot easier to see, right? We're adding what, essentially? We're adding heat, so we're going to end up with more oxygen. Right? It's going to shift if you add heat. If you would have, I think a better question would have been, put it in an ice bath. Make it cold. Then less, because then you're sucking away heat, right? You do less. Okay, so that's the game you're going to be playing a lot in the homework. They also have some general questions like this. More like a chemical engineering thing. The heat thing? All right. The heat thing, if it's positive, the technical word for positive delta H was endothermic. And endothermic means, that's the weird one. That's where heat's over here. This is, endothermic is the one where you take the pad and you break it and then the thing gets cold. So heat's a reactant. So with this, and try to disregard the word heat. Just think of reactants and products. And think, do I have too much reactant or do I have too much product on each one of these? That works for every single one. So if you're saying you're increasing the temp, well, then just look and find where heat is. Heat's a reactant, so I've got too much reactant. So it has to shift towards products. Then you look and see, oh, oxygen's a product, so that means more. Same idea with the pressure. If you increase the pressure, well, look at both sides. Well, I've got less gas molecules on the reactant side. So that's where it's going to shift if I increase the pressure.
So on the other example, the heat was on the product side?
Yeah, because it was negative. Yep. Okay, so with that thinking in mind, try 81. So what you need to do to answer 81 is circle high or low temp, circle one of those, and circle high or low pressure. Or I guess no effect is also a possibility. Kind of like a chemical engineering thing. What do you need to do? What conditions do you want so that you get, what do they want? Optimum yield of nitrogen monoxide. For some reason, they want this nitrogen monoxide. They want a lot of it. They want a lot of that stuff. So what pressure and what temperature conditions would really help you out, according to Le Chatelier? You're trying to get that equilibrium to shift towards these products. And the only thing you can mess with is temperature and pressure.
So we're doing it for ammonia or for?
No, they want nitrogen monoxide.
I know we want that one to be bigger, but it says by the oxidation of ammonia we use it.
Oh, they're just saying that's just a lot of verbiage. They could have just said, hey, how do you get the maximum NO out of this? But they just kept going by the ammonia reacting with oxygen. So don't really worry about all the verbiage. Just realize what you're after. You're after nitrogen monoxide. Okay, Alyssa. For temperature, would you have your little reaction vessel? Does it not matter? Or would you make it really hot? Or would you make it really cold if you want to get the maximum amount of NO? Okay, you hear her? She said heat's over here. You're good so far. Very good. Make it really, really cold, because then you don't have enough product. It has to shift to get more product so you can get that K back. So it's going to make even more NO. All right, here's the fun one. Pressure. This is a hard one, Mia. You have a 33.3% chance, though. What was the logic? First, you figured out what? Okay, so how many gas molecules over here? 10. And over here you got 9. I agree. I agree so far. Okay. So you want things to shift to where there's 10 gas molecules, or do you want them to shift where there's 9 gas molecules? I don't know. What are you after? You're after what compound? You're after the NO. So you want things to shift where there are how many gas molecules? Everybody? 10, right? Because the NO's on the 10 side. No big deal. That's where it is. Even within the same number of gas molecules, that's like a trick question, because then it's no effect. So that's going to be rare, right? I wouldn't be guessing that one too often. There's going to be an effect. Okay, so you want things to shift where there's 10 gas molecules. Is 10 bigger than 9? Okay, so is 10 a higher pressure or a lower pressure than 9? Higher pressure. Okay, so you want things to shift to a high pressure side. Well, if you crank up the pressure, that's just the opposite of what you want. Because if you crank up the pressure, things are going to respond to relieve that pressure and shift to 9. So you want to make the pressure really, really low. So then the system responds by trying to kick up the pressure. Okay? So make the pressure really low.
So if it was the other way, like if it was 10 on this side and 9 on that side, it would have been high?
Yes. Then you would have said high. Okay? So this is just a conceptual question. Why is this mass balance a poor description of equilibrium? Because very often people think that you have to have equal amounts of each. It's nice and balanced. I'm at equilibrium. No. Reactions are all over the place. Sometimes the reaction hardly even gets going, and it's reached equilibrium already. So you hardly have any product at all. Others, man, you can generate a lot of product. It ranges all over the place. Okay, so it's a poor illustration of equilibrium. Okay, now look at all this quiz, man. There's no math in here at all, right? But we can't allow that. So this is not going to be in your homework. What this is doing, this is preparing us for the next class period. A little algebra review. We're not going to talk about all possible algebra questions. We're just going to practice the stuff that you're going to see in class. Okay, that's what we're practicing. So we have all these variables in here, Audrey, and we have to solve for little a. Oh, man. What would you do first? Yeah. Did you see what Alyssa's doing? She's doing this kind of thing, right? Audrey, remember when? Don't let the parentheses confuse you. You can move this whole thing wherever you want in that diagonal, with that diagonal, right? So I can move these things in parentheses from one side to the other as long as I'm going along the diagonal. That's what I would do first. So in other words, move what where? Do you see what I'm trying to say? So move the what in parentheses? Move the C plus D up with the E plus F. That's the very first thing you do. So try to see these things as just C plus D's, they're together. So let's just move it up the diagonal. So I'll end up with A plus B, E plus F over G plus H. Oh, and I move that guy up, right? So I have C plus D up here. Right? Okay. Now the hard part, Kenneth. You want to solve for A, so do what now? Subtract B from both sides. You're done. It looked really bad at first, but it isn't. Right? Subtract B from both sides. So you end up with E plus F, C plus D, G plus H, and then just subtract B. Okay. Okay, Anessa. Let's see if you remember how to do this kind of thing. How would you multiply A plus B times C plus D?
FOIL, first order.
Oh, that FOIL thing. Yeah, I guess we can. If you know FOIL and you remember FOIL, do it. All the more power to you. So that's great. I would do that. You're comfortable with it. Me, I don't even remember FOIL, honestly. What am I probably going to say? Does anybody know what I'm going to say? I'm going to take A and multiply it through. Then I'm going to take B and multiply it through. I'm done. So if you like FOIL, you do your FOIL. Is that FOIL?
Yeah.
Oh, FOIL is kind of like multiplying one by the other, then adding the middle guys and.
FOIL is A times C.
I don't know.
A times D plus B plus C plus B plus
So-
D. It's the exact same thing.
All right. Well, okay. If everybody sees it, then let's all say it at the same time. This is going to equal what? A times
C.
plus AD plus BC plus
That's FOIL.
BD. That's FOIL. That's not what I thought. Okay. Not bad. Okay. So what we need to do is mess with this stuff. Now I gave you some answers. Now we're taking another step here. What we need to do is get these equations. I'm giving you them. They look like this. We need to rearrange them so they look like this. All right? We need to rearrange it so that 0 equals. 0 can be on either side. Doesn't matter. Make it so that 0 equals ax squared plus bx plus c. So a, b, and c are just numbers. But the important part is you got an x squared, an x, and a c. And then how do you figure out what x is? You substitute those little coefficients a, b, and c into here. You do that, here's your answers. You always get 2 of them. Okay? And we don't care what makes sense for the answers, what doesn't make sense. We're just after the math here. Okay. Here's our first equation. Let's do this together now. Let's pick on, back to Steph. Steph, here's the goal. Here's where we're starting. So what would you do first? Yes, she's bringing what she did in her head. She actually, I don't know if she realized it or not, she put parentheses around this thing. Because she sees them as being together. She's moving that whole thing up there with the 500. Do you see that? So she mentally, and it really helps to do this, to put parentheses around things. Oh, I'm going to move that up with the 500. That's a great thing to do first. 500 times 0.5 minus x equals 2x quantity squared. Okay. It's a good first step. Jose, now what would you do? If you do that, then what? Remember your goal. Your goal is ax squared plus bx plus c equals 0.
Multiply.
Yeah, multiply. That's a good one. Multiply that 500 through. Sounds good to me. So 500 times a half is 250 minus 500x equals 2x quantity squared. Okay, Andrea, now what could we do? I wouldn't take the square root of both sides because that would get rid of the square. But remember, and that's, you're right, but that would help simplify. But remember the goal. The goal is you want a square. Move what over to what side? Subtract the. What can we simplify this to? 4 times x squared. Yeah. I kind of broke what Andrea said into 2 steps, Cameron, because she also said to do what? Well, what would you do? What would you do now?
You would subtract 4x from each side.
You can subtract 4x squared from both sides, and then you're going to have a what over here? Negative 4x squared plus 250 minus 500x. You've got your a, b, and c. It's just that your a is going to be a negative 4. Who cares? It can be negative. You've got calculators. You don't care whether you have a, b's, and c's as positive or negative. It's just that a lot of people like to have positive a's. I'm just telling you. A lot of people like to have positive a's. Then there's less things they got to plug into their calculator. So it really doesn't matter. So whether you bring the 4x squared over here and make it negative, or bring these 2 guys over here, it doesn't matter. You just got to have a 0, and you have your a, b's, and c's. So I'm going to bring it over this way. Okay. It looks like more work, and it probably is, than what Cameron said, but I'm used to just not having to push minus signs for a, but it really doesn't matter. Okay. And it is kind of nice to have positive a's, because see how you've got a 2a in the bottom in getting your answers? If you have a negative a, you got to remember to plug in that minus sign down there. And that's not so easy to remember sometimes. Okay. Point is, now you know what your a, b, and c are. What are they? Bowdy, what's your a, b, and c here? Yeah, a is 4, b is 500, and c is negative 250. So now you've got your calculator, so we use it and plug them in. Plug them into what? Our equation up there. So we've got negative b plus or minus square root b squared minus 4ac all over 2 times a. So negative 500 plus or minus. So I got about 504 here. When I took the square root, I got about 504. Okay, make sure you can get that. And make sure you can get that on this calculator, because this is the one that you're being allowed to use on the quizzes and exams. So the square root is that shift square root button. And there's two answers, because you can do the plus 504 divided by 8, and then you do minus 500 minus 504 divided by 8. And you should get those two answers up there, right here. You should get a half or a negative 125.5. Work, Jose? Okay. So this handout is part of the homework. So you've got a lot to work on. Do you see why we're doing this? Do you see where this is coming from? It's coming from that. What we're doing is we're doing the math for ice. Here's our K, like in this next one. That 50 is going to be our K. Then we've got products over reactants from our ice table. That's where this is coming from. Okay. Yes, drum. So take, how to get the 0.5, you mean? So take negative 500 plus 504, you get 4. Divide it by 8, 4 over 8 is a half. And then the other one, negative 500 minus 504 is a negative 1,004. Divide it by 8, you get negative 125.5.